So therefore, if you are trying to realize a high quality factor biquad, then you find that you will have a lot more trouble with Q, with the gain bandwidth product of the op amp. For example, if you are trying to realize a Butterworth filter, right? We know that the ideal Butterworth response, if I plot it on if I plot it, should do something like this. Let us say it is a high order Butterworth filter. So it cuts off, virtually like a brick wall, all right. And the omega naught of all the poles is the same for a Butterworth filter, and the quality factor, as you know, right, there will be the sharp cutoff is basically the consequence of having a high quality pole pair. Now, and there are other pole pairs also. So if you recall, the Butterworth poles are basically distributed around a circle, right, something like this, blah blah blah. Okay. So which of the pole pairs is the most problematic as far as gain bandwidth product of the op amp is concerned? Yeah. These are the guys whose Q is going to get enhanced by the largest amount, because that 1 minus 2 omega naught Q by omega u is in the denominator, right. Okay. So what do you think the non-ideal response should look like? All the Qs are enhanced, but the highest Q pole pair's Q is enhanced by a lot more, right. So what do you think you will see if you basically you would expect that, oh well, the gain everywhere is greater than intended, right, and at the band edge it does. All right. Okay. And and while we have discussed all these results for a second order biquad, as I mentioned, right, this is a general result, okay, where this holds for an arbitrary transfer function if all the integrators are replaced by something else, right. And let me show you a picture of what happens with a high order filter. So for example, this is the pole zero map of a filter, which is supposed to give what is called an equiripple response, all right. And it is a high order filter whose magnitude response is supposed to be like this, okay. Those of you who are taking analog and digital filters, you probably have heard of Chebyshev filters, but I mean, that is just another way of approximating the ideal brick wall. And it turns out that again on the S plane, the pole zero map will be something like this. It just turns out that this actually is a 1, 2, 3, 4, 5, 6 is a 12th order Chebyshev filter. So basically there are a whole bunch of poles like this. That is what is going to give you that brick wall. This is the j omega axis, okay, and this is the negative sigma axis, right, and this is the 3D plot which corresponds to the magnitude response. I mean, the xy plane is basically the complex plane, right, and what do these correspond to? Those are the pole frequencies at which the magnitude response goes to, h of s goes to infinity, but we are interested in finding the magnitude response. So what do? We slice this along the j omega axis, and the ideal response that you get is basically the one shown in red here. I don't know if you are able to see it, right, that is this guy, right, and it does what it is supposed to do as advertised. Now, when all the integrators are non-ideal, what happens? We are going along, we are evaluating the same H ideal of S, but along a trajectory which is, whatever, it's j omega minus omega square over omega u, and as you can see, we are now going along this path as shown in the magenta curve, right, and therefore you can see that you're basically at the passband edge, right. You're now kind of scaling the foothills of the mountain, right. So the peak response will peak. So basically we'll see the response will peak at all frequencies, correct, okay, because the quality factor corresponding to every pole is increased, pole pair is increased. However, the enhancement is the highest with respect to the pole pair which already has the highest quality. Does it make sense? And here is a better view. So as you can see, hopefully you get a better view now, right. So this is the ideal transfer function, ideal magnitude response, and this is the actual one with non-ideal op-amps. Okay. Now looking, using this as a visualization, can we comment on what happens above? Of course, at the passband edge, you will see significant peaking in the magnitude response. Well, what do you think will happen in the stop band? Are we doing worse, or are we doing better, or are we doing the same? Deep in the stop band, what do you think will happen to the attenuation? Remember, deep in the stop band, what we are evaluating is, in the ideal case, we are going along the j omega axis like this and evaluating the surface, somewhere here, right. Okay. Now what are we doing? We are going along on that cut there, which kind of does, keeps going somewhere there on the in the S plane, right. What comment can you make about the response there versus the response here? Which is farther away from the poles? Pardon? No, think carefully. If you come back here, right, we are interested in, the stop band response again is gotten by finding the distance from a point somewhere along this that curve to both P1 and P1 star, right. As omega tends to infinity, right, where is for a large omega, if you remained on the j omega axis, you would be somewhere here. If you went off like this, you would be somewhere there, right. So which distance is larger? The non-ideal case, right. So what comment can you make about the stop band response? At very, very high frequency, asymptotically as the frequency response, frequency approaches infinity, when you have a non-ideal op-amp, okay, the attenuation is more, but is that surprising or it's not surprising? Oh yeah, well, the op-amp is totally dead, right. So in other words, the op-amp is not fast at all, and the gain is its gain is so small compared to 1 that the integrator, as you can see, the integrator's magnitude response is at high frequency was in the ideal case only going as omega naught over S. Now it is at high frequency, it is attenuated by a further factor of 1 by 1 plus S over omega u. So it seems reasonable that the attenuation at high frequencies is much smaller. All right. Okay. So the question now is, okay, well, we know what happens. Now we need to figure out what do people do to fix it, right? Remember, well, you stare at this equation and say, well, q hat is q divided by 1 minus 2 omega naught q by omega u, all right. So, what do you think you can do to fix this? Well, you know, the easiest thing to do is to say, I will give me omega naught is omega u is infinity, right? Then that, as you know, is a technological limitation. I mean, evidently, you know, the transistors we make can't, you know, work at infinite speed. The other thing, as he suggested, is to say, oh well, we know that if we shoot for q, you will get a q hat which is actually higher. So, you know, what is the common sense thing to do? What is the common sense thing to do? Well, you basically shoot for a q which is lower. I mean, you know, I mean, using this equation, you know what q to shoot for, so that with finite gain bandwidth, the response is the enhanced q is is exactly what you want. Okay. What comment can you make about, you know, is that what comment can we make about the robustness of such an approach? The omega naught times q is fixed, right? What varies in practice is the unity gain bandwidth to the op amp, you know, it can change with temperature and process and all this other stuff, right? So, if you are counting on the omega u, so that this factor, I mean, the fact that you are pre-compensating for q enhancement basically means that you know that this factor is reliable, right? That is only possible if the omega u does not change over temperature and so on. In practice, you know, I mean, you know, you get what you get, okay. So, if omega u varies, well, the q that you get also varies, and therefore, the response also will vary. There have been other clever ways of trying to fix this problem, right. So, this way of adjusting the q's a priori for the gain bandwidth of the op amp, that is called pre-distortion of the filter transfer function, right. And you know, the idea is very simple. We know that if we shoot for this, you get something like this. So, the logical solution would be to say, okay, well, you know, let us presume that I am shooting for this, okay. Then q enhancement will cause this to go and become the black, all right. So, that is one way of doing it, and you know, the problem with pre-distortion is basically pre-distorting the filter transfer function is basically that you now rely on how good our estimate of does it make sense, people? Now, the next thing that I would like to draw your attention to is the following. I mean, this is one approach, and obviously, you know, it's okay, but you know, there is an issue with robustness. Again, as I said, there has been, you know, a whole lot of workarounds for this problem. I will discuss just one simply because we have already seen you know, this aspect as far as when we did M&A. Remember that we said when we were discussing the modified nodal equations, we said that, oh well, in a circuit with ideal op amps, so if you look into our biquad, this is R, this is R, this is R, and this is C. And if this is a op amp is both the op amps are ideal, the integrated transfer function will be VO by VI, which happens to be minus plus 1 over SCR. When we were discussing modified nodal analysis, we said that if you have a network with ideal op amps, right, you can, well, we break this connection, you can break this connection, right, connect this here and connect this here, and oh sorry, oops. So, this must connect to here and this must connect here, all right. If you do this, the transfer function does not change, correct. Okay. So, if you kind of, I am going to skip the connections and just show you the final result. It turns out to be just simply redrawing the picture. This is VI, this is C, this is R, and this is V. And what should we do as far as remember, we have to figure out the negative feedback signs, and then it turns out that this is the inverting amplifier. So, you need plus and minus here to get a negative feedback around this op amp. So, this is this also is an inverting integrator, a non-inverting integrator if the op amps are ideal. So, but when the op amps are real, there is no I mean there is no reason to believe that this will give you the same transfer function as the earlier one, right. And it turns out, and I will give you the intuition behind that, it turns out that this gives you an integrated transfer function which has got some interesting property. Remember, if this op amp is non-ideal, what comment can you make about the transfer function from VO to what is fed back? That is, from this point to this point, what comment can you make about the transfer function there? Pardon? Yeah, I know. Where is the pole? At what frequency is the pole? What is the transfer function? Minus 1 divided by 1 plus, no, think carefully, 2s over omega u. You have seen this in your earlier classes, the feedback factor around the op amp is half. So, the gain, I mean the bandwidth will be 1/2 the unity gain bandwidth. So, the transfer function in the feedback path is minus 1 by 1 plus 2s over omega u, all right. I will so in the feedback path, let me draw your attention to our standard negative feedback system, right. So, this is A and this is the feedback factor is f, right, and let us say you had some transfer function from the input to the output. Now, if I put in a pole here of 1 by 1 plus 2s over omega u, what comment can you make about how the closed loop transfer function will change? It will be it will show up as a 0. So, the transfer function will so whatever transfer function you had earlier, correct, it will now have a 0 because the feedback path has been how does this compare with the original integrator? What is the difference between this and that? The current here is approximately V naught times SC. Now, what is the current here? Yes, what is it? It is V naught times SC times 1 over 1 plus, apart from the negative sign, there is basically 1 plus 2s over omega u, correct? So, what comment can you make about the transfer function that you get? So, effectively in the feedback path, you have inserted a pole, and as he pointed out, the closed loop transfer function is simply proportional to 1 over the feedback factor times the loop gain by loop gain plus 1, right. So, at sufficiently to first order, therefore, the transfer function of this integrator is 1 over SCR times 1 by 1 plus S by omega u, which is what you would get if this character wasn't around, right, multiplied by 1 plus 2s over omega, right. So, this is an approximation. In your assignment, you will go and prove it. Okay. So, what is this giving you? How does it compare with the original integrator, with the non-ideal op amp? This had minus 1 over SCR times 1 by 1 plus people. Derwin, what is it? I can't hear you. S by omega u, all right, okay. And this guy is now, one integrator is this, the combination of inversion and integration, which was giving us a non-inverting integrator earlier, right, is 1 by SCR times 1 plus S over omega u times 1 plus 2s over omega u, all right. So, what do you see therefore? Well, if you evaluate, we have a cascade of two integrators and what do you call a damped integrator and an non-inverting integrator. Earlier you would you would not get these factors. Now, in one of the integrators you get this factor, in the other one you basically get this factor. And what comment can you make about when you multiply the two of them together? To first order, you basically see that 1 plus S by omega u whole square is approximately 1 plus 2s by over omega u. You have 1 plus 2s by omega u in the numerator, and therefore, the two of them to first order cancel, right. Another way of thinking about it is that there is this creates phase lead. You are putting a lag in the feedback loop, in the feedback factor, causes a lead in the closed loop transfer function, and therefore, the two of them the lag of this, the lead of this basically cancels the lag of the other integrator, and you basically get something which is to first order independent of omega u, right. And the omega u therefore, and what do you call because the phase lead and the phase lag are caused by the op amp, the same kind of op amp, it follows that, well, if the op amp gain bandwidth changes a little bit, well, the phase lead changes, the phase lag also changes by the same amount and the two cancel, right. So to first order there is cancellation of gain by product effects. Is this clear? All right.